Today we are going to learn about data preprocessing for effective model training. You will master techniques like normalization, handling missing values, and encoding categorical variables to improve your model's accuracy and efficiency.
Welcome to our exploration of data preprocessing for effective model training. In today's session, we'll dive into the crucial role that data preprocessing plays in the world of machine learning. Proper preprocessing can significantly enhance the accuracy and robustness of your models. We'll cover essential techniques such as normalization, handling missing data, encoding categorical variables, and more. By the end of this video, you'll be equipped with the knowledge to preprocess data effectively using Python libraries, ensuring your models perform at their best. Let's get started. Data preprocessing is a fundamental step in the machine learning pipeline that involves transforming raw data into a clean, usable format. This process is vital because the quality of your input data directly affects the performance of your machine learning models. Preprocessing helps in identifying and removing noise and anomalies, which can otherwise lead to inaccurate predictions. It prepares data for analysis by cleaning, transforming, and organizing it into a structured format. This not only enhances the model's accuracy but also its robustness, ensuring it performs well when exposed to new data. Understanding the role of data preprocessing sets the foundation for building effective models.
Missing data is a common issue that can drastically affect your model's performance. First, it's crucial to identify missing data points within your dataset. Common methods include checking for NA-NS or using visualization tools to spot gaps. Once identified, several imputation strategies can be applied. Simpler methods like replacing missing values with the mean, median, or mode of the column offer quick fixes. However, they might not always provide the best results. Advanced techniques such as k-nearest neighbors, KNN, or multiple imputation by chained equations, MICE, consider correlations between different features, providing more accurate imputations. The choice of methods should be guided by the dataset's nature and the model's end goal.
Normalization and standardization are techniques used to scale data features so they fit within a specific range, typically improving model training dynamics. Normalization scales all numeric variables in the range of 0 to 1. It is useful when you need your data to have a specific scale, often seen in scenarios involving bounded data like images. Standardization, on the other hand, scales data to have a mean of 0 and a standard deviation of 1, making it suitable for algorithms that assume normally distributed data, like SVMs and linear regression. Both methods can enhance model convergence, especially for algorithms sensitive to feature scaling. Always consider your specific use case when choosing between normalization and standardization. Categorical variables represent a critical part of many datasets, and encoding them appropriately is essential for model training. The most common methods include one-hot encoding and label encoding. One-hot encoding transforms each category into a binary vector, which is useful for algorithms that do not assume any order among categories. Label encoding assigns a unique integer to each category, suitable for ordinal data where order matters. However, label encoding can mislead models that treat numerical values with inherent order, potentially skewing results. When dealing with high cardinality many unique categories, consider techniques like feature hashing to reduce dimensionality while retaining information. Choosing the right encoding strategy depends on the dataset's nature and the chosen algorithm. Feature scaling is a crucial step that can significantly impact your machine learning model's performance. It ensures that all features are given equal weight in the model's learning process, preventing features with larger ranges from disproportionately influencing the outcome. This is particularly important in distance-based models like KNN or algorithms involving gradient descent. Common techniques include min-max scaling and standardization. Min-max scaling scales data within a specific range, usually 0 to 1, while standardization adjusts features to have a mean of 0 and standard deviation of 1. Proper scaling can prevent biases and improve the convergence speed and optimization algorithms, leading to better and faster model training. Imbalanced datasets occur when one class significantly outnumbers others, often leading to biased models favoring the majority class. This imbalance can skew model accuracy and reduce its ability to generalize. Strategies to handle imbalances include resampling techniques such as oversampling the minority class or undersampling the majority class. Synthetic minority oversampling technique, SMOT, is an advanced method that generates synthetic samples from the minority class, improving balance without duplication. Properly addressing imbalanced datasets is crucial in achieving reliable, unbiased models that perform well in real-world applications.
Python offers a rich ecosystem of libraries that simplify data preprocessing. Pandas and scikit-learn are among the most popular, providing robust tools for handling missing data, encoding categorical variables, and scaling features. With Pandas, you can easily identify and fill missing values or apply transformations to your data. Scikit-learn offers convenient preprocessing modules for normalization, standardization, and encoding, often integrating smoothly with its machine learning models. By utilizing these libraries, you can create preprocessing pipelines that streamline your workflow, ensuring consistent, repeatable processes. We'll walk through code examples illustrating each preprocessing technique, equipping you with practical skills for effective data preparation. Evaluating the impact of preprocessing steps is crucial to understanding their effect on your model's performance. Key metrics like accuracy, precision, recall, and F1 score provide insights into how well your model performs before and after preprocessing. By comparing models trained with raw data against those trained with preprocessed data, you can assess the value added by each preprocessing step. Look for improvements in model accuracy and reduction of overfitting as indicators of effective preprocessing. Analyzing these results allows you to iterate on your preprocessing strategy, fine-tuning your approach to optimize model performance. We've covered a comprehensive range of data preprocessing techniques essential for effective model training. From handling missing data to encoding categorical variables, normalizing, and feature scaling, each step plays a crucial role in preparing your data for machine learning. Preprocessing not only enhances model accuracy but also ensures robustness and generalizability. As you continue your journey in data science, practice these techniques using Python libraries, and don't hesitate to explore more advanced topics like feature engineering and data augmentation. Thank you for joining us, and happy coding!